Welcome to How the Heavens Go. I'm your host, Mark Lesmeister. Last year for Christmas, my son gave me this cool Lego Technic model kit. It's actually a working orrery, which is a device that shows the motion of one or more celestial bodies. If you've followed my channel for any length of time, you probably know where this is going. While constructing the model, we're going to talk about the physics and history of our understanding of the motions of the heavens. If you're into that sort of thing, I have some other video series that are similar to it. I have one called The Spirit of Apollo, where I construct a Lego Saturn V model and talk about the physics and history of the moon landings. I also have a series called Throwing Stones, where I construct some model catapults, both small and large, and discuss the physics and history of catapults. In this series, we're going to see how we constructed the model from the kit. We're also going to talk about various motions of the heavens and see how our understanding of those motions has changed over time using the model. Don't worry, my plan is not to discuss the entire history of astronomy. I just want to show some things that I think are interesting, and I hope you find them interesting as well. If you come away from this series with a greater appreciation for and understanding of God's creation, my goal will have been met. In this video, we will consider the various motions or apparent motions of the sun. The most obvious of those motions is daily motion. Every day, the sun appears to rise in the east, somewhere, more on that later, move across the sky and set in the west. This is called diurnal motion, from the Latin word for day, dies. If you are north of the Arctic Circle or south of the Antarctic Circle, there will be days when the sun doesn't rise and other days when it doesn't set, but just appears to circle the skies. The moon and stars also have diurnal motion. Again, depending on your location, on some days, some of the stars might just appear to circle the skies instead of rising and setting. Ancient astronomers often classified celestial objects, that is, things they could see in the heavens, into two categories, often called the fixed stars and the wandering stars. The fixed stars were called that because, though they have diurnal motion, they maintain fixed positions relative to each other. Thus, groups of stars form unchanging, recognizable patterns called constellations. Often these patterns came to be associated with important mythological or religious figures, such as Orion the Hunter from Greek mythology. Celestial objects that did not keep their same position relative to each other, or the fixed stars, fell into a different category. The ancient Greeks called these objects asteres planetae, or wandering stars. That is where we get the word planet. The asteres planetae included the sun, the moon, as well as the 5 planets other than the Earth visible to the naked eye: Mercury, Venus, Mars, Jupiter, and Saturn. It might seem odd to call all the other moving bodies stars, but remember that the ancients didn't have the nice pictures of these objects courtesy of NASA that we have. With bare eye astronomy, except for the sun and the moon, all these objects just look like bright dots in the sky, much like the other stars. Let's consider the motions that the sun has beyond its diurnal trek across the sky. First, the path that the sun appears to follow each day shifts over the course of a year. From late December to late June, the path of the sun moves farther north each day. As the path shifts north, the days get longer in the northern hemisphere, meaning the time between sunrise and sunset gets bigger. In the southern hemisphere, the days get shorter. The line marking the northernmost latitude the sun's path reaches is called the Tropic of Cancer. At locations north of this line, the sun will never be directly overhead. It will always be at least a little bit south. However, the farther north the sun gets, the more direct the sun's rays are at those locations. The sun's path reaches the northernmost excursion on around June 21st. This is known as the June solstice, or the summer solstice when referring to the northern hemisphere, and the winter solstice in the southern hemisphere. After the June solstice, the sun's path begins creeping south. In the northern hemisphere, the days get shorter. It reaches its farthest southern excursion, shown on the map as the Tropic of Capricorn, on the December solstice, around December 21st. In addition to the diurnal and north-south motion of the sun, ancient astronomers noticed that over the course of a year, the sun shifted in position relative to the constellations, at a rate of almost 1 degree eastward each day. For example, let's suppose that at some point in time the sun is in front of the constellation Aquarius during its daily trek across the sky. Of course, when the sun is out, it's too bright to see the stars that appear around it, but ancient astronomers knew what constellations would normally be surrounding that area that the sun was occupying. So each night it would appear a little bit farther eastward relative to that constellation. So a week later, it might look like this, a little bit farther to the east in Aquarius. And then a week later, it might look like this. And a week later, like this. Eventually, it's going to be in between the constellation Aquarius and Pisces. And so a few weeks later, it eventually ends up firmly in the constellation Pisces. The apparent path of the sun over the course of a year, as seen from the Earth, is called the ecliptic. The constellations that lie along the ecliptic often took on special significance in ancient cultures. The changing path of the sun, with the resulting changes in intensity of sunlight and length of days, is what gives us our seasons. That there was a connection between the sun's motions and the seasons was not lost on the ancient peoples of the world. Many cultures established calendars based on the motion of the sun. All over the world we find places where the apparent motions of the sun were observed for agricultural reasons, religious reasons, or both. One such place is the Stonehenge Monument on the Salisbury Plain in Wiltshire, England. My son James and I watched the sunrise on the morning of the winter solstice at Stonehenge in 2016. Even here in the Meridiana subdivision of Iowa Colony, Texas, where I live, we have a solar calendar. The Meridiana solar calendar is located at the Oasis Village, one of our community centers. It consists of a tall central tower and various diagrams embedded in the walkways surrounding the tower. The central tower has a ring embedded in it that looks like the corona of the sun. Inside that ring is a flat disc with a hole cut into it. This produces a bright spot in the shadow of the disc. This line running down the center of the diagram in front of the central tower is called the meridian. Meridian comes from meridies, which is Latin for midday. This line marks the position of the sun at midday. Meridian is where the Meridiana community gets its name. I took this video on a sunny day near noon. You can see the meridian line down the center of the diagram in front of the central tower. The coronal ring and the embedded disc cast a distinct shadow on the ground. The markings along the meridian show where the shadow will fall at the first of the month for each month of the year. You can see that the bright spot in the shadow, made by the hole in the central disc, falls just beyond the marking for December 1st, as I made this recording on December 2nd. The bright spot is slightly to the left of the meridian because I made the video at a few minutes before local noon, meaning the time at this location where the sun is at its highest point in the sky. We will look at the astronomical basis for the sun's apparent motion in a later episode. But for now, let's look at the first stage of our Lego model. So we're going to start with bag 1, which makes mostly the base of the model. And so here we go. As expected, this first part of the build involved completing the stationary base of the model. We can imagine this as representing the fixed stars, which stay more or less in one place in our simplified model. So that is it for this episode. Next time we will build some more of the model, and we'll talk about some of the systems early astronomers came up with to explain the motions that we saw in this episode. Until then, look to the stars.